all know very well, you are looking at the pictures of lenses and their converging and diverging actions. Knowingly and unknowingly, these lenses have become a compulsory part of the so-called modern and technical lifestyles. Now that we cannot do without them, it is good to know the minute and mathematical details of the lenses, especially for science students, so that we can put them to proper use in our labs, factories and lives.
Dear students, आज ऑप्टिक्स ਦੀ ਇੱਕ ਹੋਰ ਕਲਾਸ ਵਿੱਚ ਤੁਹਾਡਾ ਸਵਾਗਤ ਹੈ। ਅੱਜ ਦੀ ਇਸ ਕਲਾਸ ਵਿੱਚ ਅਸੀਂ ਲੈਂਸ ਮੇਕਰਸ ਫਾਰਮੂਲਾ ਦੀ ਡੈਰੀਵੇਸ਼ਨ ਤੇ ਵਿਚਾਰ ਕਰਾਂਗੇ। ਲੈਂਸਸ ਜਿੱਥੇ ਵੀ ਵਰਤੇ ਜਾਣ, ਇਹਨਾਂ ਦੀ ਸਹੀ ਵਰਤੋਂ ਕਰ ਸਕਣ ਲਈ ਅਜਿਹੇ ਮੈਥਮੈਟੀਕਲ ਪਾਰਟਿਕੂਲਰਸ ਬਾਰੇ ਜਾਣਨਾ ਜ਼ਰੂਰੀ ਹੈ। ਅਸੀਂ ਲੈਂਜ਼ਾਂ ਬਾਰੇ ਬੁਨਿਆਦੀ ਗੱਲਾਂ ਦੀ ਦੁਹਰਾਈ ਤੋਂ ਬਾਅਦ ਦੋਵੇਂ ਤਰ੍ਹਾਂ ਦੇ ਯਾਨੀ ਕਨਵੈਕਸ ਅਤੇ ਕਨਕੇਵ ਲੈਂਜ਼ਾਂ ਲਈ ਇਸ ਫਾਰਮੂਲੇ ਦੀ ਡੈਰੀਵੇਸ਼ਨ ਬਾਰੇ ਜਾਣਾਂਗੇ। ਇਸ ਲੈਸਨ ਦੀ ਡਿਟੇਲ ਵਿੱਚ ਜਾਣ ਤੋਂ ਪਹਿਲਾਂ ਮੈਂ ਤੁਹਾਡੇ ਨਾਲ ਅੱਜ ਦੇ ਵਿਸ਼ੇ ਦੇ ਸਿੱਖਿਆ ਉਦੇਸ਼ ਸਾਂਝੇ ਕਰਾਂਗੀ।
After the completion of this lesson, the students will be able to recall the various shapes of lenses, draw the ray diagrams for image formation with lenses, define and draw the various shapes of lenses, derive the lens maker's formula for a convex lens. Derive the lens maker's formula for a concave lens.
ਵਿਦਿਆਰਥੀਓ, ਅਸੀਂ ਲੈਂਜ਼ਾਂ ਦੀ ਡੈਫੀਨੇਸ਼ਨ ਅਤੇ ਡਾਈਵਰਸ ਸ਼ੇਪਸ ਬਾਰੇ ਦੁਹਰਾਈ ਨਾਲ ਸ਼ੁਰੂ ਕਰਦੇ ਹਾਂ। ਤੁਹਾਨੂੰ ਚੰਗੀ ਤਰ੍ਹਾਂ ਯਾਦ ਹੋਵੇਗਾ ਕਿ ਲੈਂਸ ਹੁੰਦਾ ਕੀ ਹੈ। ਲੈਂਸ ਇੱਕ ਟ੍ਰਾਂਸਪੇਰੈਂਟ ਰਿਫਰੈਕਟਿੰਗ ਮੀਡੀਅਮ ਹੁੰਦਾ ਹੈ ਜਿਸ ਦੇ ਦੋ ਸਫੈਰਿਕਲ ਸਰਫੇਸਿਸ ਹੋ ਸਕਦੇ ਹਨ ਜਾਂ ਇੱਕ ਸਰਫੇਸ ਸਫੈਰਿਕਲ ਅਤੇ ਦੂਜਾ ਪਲੇਨ ਹੋ ਸਕਦੇ ਹਨ। ਆਮ ਤੌਰ ਤੇ ਵਰਤੇ ਜਾਂਦੇ ਸਫੈਰਿਕਲ ਸਰਫੇਸਿਸ ਕਨਵੈਕਸ ਜਾਂ ਕਨਕੇਵ ਸਰਫੇਸਿਸ ਹੋ ਸਕਦੇ ਹਨ ਅਤੇ ਇਹਨਾਂ ਨੂੰ ਬਣਾਉਣ ਵਾਲਾ ਮੀਡੀਅਮ ਆਮ ਤੌਰ ਤੇ ਕੱਚ ਜਾਂ ਗਲਾਸ ਹੁੰਦਾ ਹੈ। ਇਨ ਸ਼ਾਰਟ, ਇਹ ਇੱਕ ਟ੍ਰਾਂਸਪੇਰੈਂਟ ਮੀਡੀਅਮ ਹੈ ਜੋ ਕਿ ਦੋ ਸਰਫੇਸਿਸ ਦਾ ਬਣਿਆ ਹੁੰਦਾ ਹੈ ਜਿਨ੍ਹਾਂ ਚੋਂ ਘੱਟੋ ਘੱਟ ਇੱਕ ਕਰਵਡ ਹੋਣਾ ਚਾਹੀਦਾ ਹੈ। ਇਹਨਾਂ ਦੀਆਂ ਦੋ ਮੁੱਖ ਕੈਟਾਗਰੀਜ਼ ਹਨ, convex lenses ਅਤੇ concave lenses. The convex lens is thicker at the center and thins out towards the edges, while the concave is just reverse. That is, it is thin at the center and thickens out towards the edges. Also, a convex lens has a converging capability, while a concave lens has a diverging capability. I believe you would also be remembering that each of the convex and concave lenses can be subdivided in three groups each. Let us see them.
The three types of convex lenses are a biconvex lens, a plano-convex lens, and a concavo-convex lens. Though the names and their diagrams must have made a clear picture in your minds, but still, let me tell you that a biconvex lens has both its surfaces as convex. A plano-convex lens has one of its surfaces as plane and the other as convex, whereas in a concavo-convex lens, one of the surfaces of the lens is concave while the other is convex. Similarly, the three types of a concave lens are a biconcave lens, a plano-concave lens, and a convexo-concave lens. You would have known the meanings of the names of their shapes after looking at the diagrams.
Some important terms related to lenses are principal axis, that is defined as a straight line passing through the centers of curvatures of two surfaces of a lens, and then the optical center, which is a point lying on the principal axis of the lens so that a ray of light whose refracted path passes through this point will have its emergent path parallel to the direction of the incident ray. The ray will suffer only some lateral displacement. The optical center C of the lens divides its thickness in the ratio of the radii of curvature of two surfaces of the lens. Thus, Cp1 by Cp2 is equal to P1C1 by P2C2, which is equal to R1 by R2, where R1 and R2 are the radii of curvature of the two surfaces of the lens. For a thin lens, however, the optical center is taken as a point lying on the principal axis so that a ray of light passing through it does not suffer any deviation from its path, that is, it goes undeviated without even any lateral displacement. And now we need to define the principal focus. ਜਦੋਂ ਲਾਈਟ ਦੀ ਇੱਕ ਬੀਮ ਲੈਂਸ ਦੇ ਪ੍ਰਿੰਸੀਪਲ ਐਕਸਿਸ ਦੇ ਪੈਰਲਲ ਦਿਸ਼ਾ ਵਿੱਚ ਲੈਂਸ ਦੇ ਇਨਸੀਡੈਂਟ ਹੁੰਦੀ ਹੈ ਤਾਂ ਕਨਵੈਕਸ ਲੈਂਸ ਦੇ ਕੇਸ ਵਿੱਚ ਲੈਂਸ ਵਿੱਚੋਂ ਰਿਫਰੈਕਸ਼ਨ ਤੋਂ ਬਾਅਦ ਇਹ ਪ੍ਰਿੰਸੀਪਲ ਐਕਸਿਸ ਦੇ ਇੱਕ ਪੁਆਇੰਟ ਤੇ ਕਨਵਰਜ ਹੁੰਦੀ ਹੈ ਅਤੇ ਕਨਕੇਵ ਲੈਂਸ ਦੇ ਕੇਸ ਵਿੱਚ ਇਹ ਪ੍ਰਿੰਸੀਪਲ ਐਕਸਿਸ ਤੇ ਕਿਸੇ ਪੁਆਇੰਟ ਤੋਂ ਡਾਇਵਰਜ ਹੁੰਦੀ ਨਜ਼ਰ ਆਉਂਦੀ ਹੈ। ਤੁਸੀਂ ਇਹਨਾਂ ਫਿਗਰਸ ਵਿੱਚ ਵੇਖ ਸਕਦੇ ਹੋ ਕਿ ਪੁਆਇੰਟ F ਪ੍ਰਿੰਸੀਪਲ ਫੋਕਸ ਨੂੰ ਦਰਸਾਉਂਦਾ ਹੈ ਅਤੇ ਲੈਂਥ CF ਹਰ ਕੇਸ ਵਿੱਚ focal length ਹੈ। Finally, we define the aperture of a lens. This is the effective diameter of its light transmitting area for a lens. Henceforth, the brightness or the intensity of image formed by a lens, which depends on the amount of light passing through the lens, will vary as the square of the aperture of the lens. Let me now take you to show the ray diagrams for image formation of objects placed at different distances from convex and concave lenses. I believe a visual will give you a better perception.
You can see an object kept between O and F in front of a convex lens. After refraction of the incident rays from the object, a virtual, erect and enlarged image is formed on the same side of the lens as that of the object. Then the object is placed at F. Now the incident rays from the object get refracted and go parallel to each other. Since the parallel rays are assumed to be meeting at infinity, the image is supposed to be real, inverted, highly enlarged and at infinity on the other side of the lens. Next, the object is kept between F and 2F in front of the convex lens. The image formed is real, inverted, enlarged and beyond 2F on the other side of the lens. Next, it is the turn to put the object at 2F. After the refraction of the incident rays, a real and inverted image of the same size as that of the object is formed at 2F itself on the other side of the lens. And now the object is placed beyond 2F. This time the image formed is real and inverted again, but diminished in size and is between F and 2F. Finally, we keep the object at infinity and receive a set of parallel incident rays. These parallel incident rays converge in the focal plane to form an almost point-sized real and inverted image on the other side of the lens. Let me now show you the image formation with a concave lens. In case of a concave lens, for any position of the object in front of the lens, the image is always virtual, erect, diminished in size and is on the same side of the lens as that of the object.
There is one important aspect, that is the lens formula. Let us have a quick reminder of this too. I have called it as a reminder as you have done it in your junior classes also. Consider this ray diagram for an object kept beyond 2f in front of a convex lens so as to form a real image on the other side of the lens. As triangles ABC and A'-B'-C are similar, BA upon B'-A' is equal to CB upon CB'. This is equation 1, but BA is equal to CP. Therefore, CP upon B'-A' is equal to CB upon CB'. This is equation 2. Again, triangle PCF and A'-B'-F are similar. Thus, CP upon B'-A' is equal to CF upon FB'. This is equation 3. From equations 2 and 3, CB upon CB' is equal to CF upon FB' equal to CF upon CB' minus CF. Using the symbols CB equal to minus U, CB' is equal to plus V and CF is equal to plus F, the equation 4 can be written as minus U upon V is equal to F upon V minus F. On cross multiplying, we get minus UV plus UF is equal to VF. Dividing both sides by UVF, we get 1 upon V minus 1 upon U equal to 1 upon F, which is the required lens formula. Lens maker formula is a relation that connects focal length of a lens to the radii of curvature of the two surfaces of the lens and the refractive index of the material of the lens. It is useful to design lenses of desired focal length using suitable material and surfaces of suitable radii of curvature. In deriving this formula, we use new Cartesian sign conventions. First, all distances are to be measured from the optical center of the lens. Second, all the distances measured in the direction of incidence of light are taken as positive, whereas all the distances measured in a direction opposite to the direction of incidence of light are taken as negative. Third, for a convex lens, focal length f is positive and for a concave lens, f is negative. The assumptions made for the derivation are: first, the lens is assumed to be thin so that distances measured from the poles of its surfaces can be taken as equal to the distances from the optical center of the lens. Second, the aperture of the lens is small. The third assumption is the object consists only of a point lying on the principal axis of the lens. Fourth, the incident ray and refracted ray make small angles with the principal axis of the lens. We know that a convex lens is made up of two convex spherical refracting surfaces. Lens maker formula is a relation that connects focal length of a lens to radii of curvature of the two surfaces of the lens and refractive index of the material of the lens. The final image is formed after two refractions, that is, at the interface of the different media twice. If you look at the diagram, P1, P2 are the poles. C1, C2 be the centers of curvature of two surfaces of a thin convex lens XY with optical center at C. Let mu2 be the refractive index of the material of the lens and that it is placed in an optically rarer medium of absolute refractive index mu1. Now, consider a point object O lying on the principal axis of the lens. A ray of light starting from O and incident normally on the surface XP1Y along OP1 passes straight. Another ray incident on xp1y along OA is refracted along AB. If the lens material were continuous and there were no boundary second surface xp2y of the lens, the refracted ray AB would go straight, meeting the first refracted ray at I1. Therefore, I1 would have been a real image of O formed after refraction at xp1y. It is clear from the geometry of the ray diagram that angle R1 is equal to gamma 1 minus beta 1 and angle I1 is equal to alpha 1 plus gamma 1. Since sin I1 upon sin R1 is equal to mu 2 upon mu 1 when angles are small, we get mu 1 I1 equal to mu 2 R1. On substituting the values of I1 and R1, we get mu 1 into alpha 1 plus gamma 1 equal to mu 2 into gamma 1 minus beta 1. On further solving, we get mu 1 alpha 1 plus mu 2 beta 1 equal to mu 2 minus mu 1 into gamma 1. For small angles, alpha 1 is equal to AP1 upon P1O. Beta 1 is equal to AP1 upon P1 I1 and gamma 1 is equal to AP1 upon P1 C1. Therefore, it can be obtained that mu 1 upon P1O plus mu 2 upon P1 I1 is equal to mu 2 minus mu 1 upon P1 C1. Let this be equation 1 since the lens has been assumed to be thin. It can be written that CC1 is approximately equal to P1 C1. Also, CO is approximately equal to P1O since the distance is against the incident ray, and CI1 is approximately equal to P1 I1. Then, using the relation between the object distance, the image distance and the refractive indices in equation 1, we have mu 1 upon CO plus mu 2 upon CI1 equal to mu 2 minus mu 1 upon CC1. Let this be equation 2. Actually, the lens material is not continuous. Therefore, the refracted ray AB suffers further refraction at B and emerges along BI, meeting actually at the principal axis at I. Therefore, I is the final and real image of O, formed after refraction through the convex lens. For refraction at the second surface, xp2y, we can regard I1 as a virtual object whose real image is formed at I. It is clear from the geometry of the ray diagram that angle R2 is equal to beta 2 plus gamma 2 and angle I2 is equal to beta 1 plus gamma 2. Since sin I2 upon sin R2 is equal to mu 1 upon mu 2 when angles are small, we get mu 2 I2 equal to mu 1 R2. On substituting the values of I2 and R2, we get mu 2 into beta 1 plus gamma 2 equal to mu 1 into beta 2 plus gamma 2. On further solving, we get minus mu 2 beta 1 plus mu 1 beta 2 equal to mu 2 minus mu 1 into gamma 2. For small angles, beta 1 is equal to BP2 upon P2 I1, beta 2 is equal to BP2 upon P2 I, and gamma 2 is equal to BP2 upon P2 C2. Thus, we can obtain minus mu 2 upon P2 I1 plus mu 1 upon P2 I is equal to mu 2 minus mu 1 upon P2 C2 as equation 3. Remember that the lens is thin. Therefore, Ci1 is approximately equal to P2I1, Ci is approximately equal to P2I, and Cc2 is approximately equal to P2C2. Now, equation 3 becomes minus mu2 upon Ci1 plus mu1 upon Ci equal to mu2 minus mu1 upon Cc2 as equation 4. If we add equations 2 and 4, we can write mu1 upon Co plus mu2 upon Ci1 minus mu2 upon Ci1 plus mu1 upon Ci equal to mu2 minus mu1 upon Cc1 plus mu2 minus mu1 upon Cc2, which can be simplified to mu1 upon Co plus mu1 upon Ci equal to mu2 minus mu1 into whole of 1 upon Cc1 plus 1 upon Cc2. This is equation 5. Using the new Cartesian sign conventions, CO is equal to minus U as this distance is against the incident ray. Ci is equal to plus V because distance is along the incident ray. Cc1 is equal to plus R1 as it is along the incident ray, and Cc2 is equal to minus R2 because it is against the incident ray. The equation 5 can now be written as mu1 upon minus U plus mu1 upon V equal to mu2 minus mu1 into whole of 1 upon plus R1 plus 1 upon minus R2, or minus mu1 upon minus U plus mu1 upon plus V equal to mu2 minus mu1 into whole of 1 upon R1 minus 1 upon R2. If we divide both the sides of this equation by mu1, we get minus 1 upon U plus 1 upon V equal to mu2 upon mu1 minus 1 into whole of 1 upon R1 minus 1 upon R2. As we know, mu2 upon mu1 is equal to mu. This equation becomes minus 1 upon U plus 1 upon V equal to mu minus 1 into whole of 1 upon R1 minus 1 upon R2. When the object on the left of the lens is at infinity, the image is formed at the principal focus of the lens. Hence, substituting U equal to infinity, V equal to F, the focal length of the lens in equation 3, we have 1 upon F minus 1 upon infinity equal to mu minus 1 whole into 1 upon R1 minus 1 upon R2, or 1 upon F is equal to mu minus 1 whole into 1 upon R1 minus 1 upon R2. This is the lens maker's formula for a convex lens. Similar to convex lens, we can derive the lens maker's formula for a concave lens as well. For concave lens, the expression is minus 1 upon U plus 1 upon V equal to mu2 upon mu1 minus 1 into whole of 1 upon R1 minus 1 upon R2. As we know, mu2 upon mu1 is equal to mu. This equation becomes minus 1 upon U plus 1 upon V equal to mu minus 1 into whole of 1 upon R1 minus 1 upon R2, or 1 upon F is equal to mu minus 1 whole into 1 upon R1 minus 1 upon R2. This is the lens maker's formula for a concave lens. Dear students, मैं हुण तुहानू एक assumption याद करवाना चाहती हैं, ਜਿਹੜੀ कि ਅਸੀਂ lens maker's formula derive ਕਰਨ ਤੋਂ ਪਹਿਲਾਂ assume ਕੀਤੀ ਸੀ। ਉਹ ਇਹ ਕਿ ਅਸੀਂ ਲੈਂਸ ਨੂੰ ਥਿਨ ਮੰਨਦੇ ਹਾਂ। ਤੁਹਾਡੇ ਦਿਮਾਗ ਵਿੱਚ ਇੱਕ ਬਹੁਤ ਵੱਡਾ ਕਿਉਂ ਹੋਵੇਗਾ। आओ मैं इस ਨੂੰ ਸਪਸ਼ਟ ਕਰਾਂ। ਅਜਿਹਾ ਇਸ ਕਰਕੇ ਹੈ ਕਿਉਂਕਿ थिक लेंसेज दी फोकल लेंथ इस गल ते निर्भर करती है कि इंसीडेंट लाइट लेंस दे केड़े फेस ते इंसीडेंट है। इस तर्क मुताबिक लेंस दी एग्जैक्ट फोकल लेंथ दी कैलकुलेशन बहुत ही डिफिकल्ट हो जाती है। After having known these calculations, I would want you to solve some questions. This will require some hard work for you. The radii of curvature of the surfaces of a double convex lens are 15 centimeter and 30 centimeter respectively, and its focal length is 15 centimeter. What is the refractive index of the material of the lens? The solution goes like this. Here R1 is equal to 15 centimeter, R2 is minus 30 centimeter, focal length of the lens is 15 centimeter, and the refractive index, that is mu, is to be calculated. The formula used is 1 upon f is equal to mu minus 1 whole into 1 upon R1 minus 1 upon R2. Substituting the values of R1, R2 and F in the formula, we have 1 upon 15 is equal to mu minus 1 whole into 1 upon 15 plus 1 upon 30, or 1 upon 15 is equal to mu minus 1 whole into 2 plus 1 upon 30, or 1 upon 15 is equal to mu minus 1 whole into 1 upon 10. This leaves us with 10 upon 15 equal to mu minus 1. This means 0.67 equal to mu minus 1, or mu is equal to 1.67. So now let us get to summarize the main aspects of what we have studied today. Lens maker's formula is a relation between the focal length of a lens, the radii of curvature of the two surfaces of the lens, and the refractive index of the material of the lens. For deriving this formula, we use new Cartesian sign conventions. All distances are measured from the optical center of the lens. All the distances measured in the direction of incidence of light are taken as positive, whereas all the distances measured in a direction opposite to the direction of incidence of light are taken as negative. Focal length is positive for a convex lens and negative for a concave lens. The assumptions made for the derivation are: the lens is assumed to be thin, the aperture of the lens is small, the object consists only of a point lying on the principal axis of the lens, and the incident ray and refracted ray make small angles with the principal axis of the lens. The lens maker's formula for both convex and concave lenses is given as 1 upon f equal to mu minus 1 whole into 1 upon R1 minus 1 upon R2. The formula is useful to design lenses of desired focal lengths using suitable material and surfaces of suitable radii of curvature. The lens formula for a lens is a relation between the object distance, the image distance, and the focal length of the lens. 1 upon v minus 1 upon u equal to 1 upon f. If the object distance and the image distance can be measured, the focal length of a lens can be easily calculated. There I end up with the teaching for today. I would want you to solve and answer some questions from what you have learned. My first question is, which physical quantities are related in a lens maker's formula? The answer is, lens maker's formula relates the focal length of a lens, the radii of the curvature of the two surfaces of the lens, and the refractive index of the material of the lens. The next question is, state the lens maker's formula. Well, you know the answer. It is 1 upon f equal to mu minus 1 whole into 1 upon r1 minus 1 upon r2, where the symbols have their usual meaning. My last question to you is, what is the significance of the lens maker's formula? The answer is, the lens maker's formula is used to design lenses of desired focal lengths using suitable material and surfaces of suitable radii of curvature. May we close the class for today now. I hope that the derivation of the lens maker's formula is well understood by you all. Thanks for attending the class carefully. Goodbye and see you next time. Dear students, ਇਹ ਤਾਂ ਚੰਗੀ ਤਰ੍ਹਾਂ ਜਾਣੀ ਹੋਈ ਗੱਲ ਹੈ ਕਿ ਹਰ ਮੈਗਨੇਟ ਇੱਕ ਡਾਈਪੋਲ ਹੁੰਦਾ ਹੈ ਅਤੇ ਆਈਸੋਲੇਟਡ ਮੈਗਨੈਟਿਕ ਪੋਲਸ ਐਗਜ਼ਿਸਟ ਨਹੀਂ ਕਰਦੇ। ਅੱਜ ਅਸੀਂ ਮੈਗਨੈਟਿਕ ਡਾਈਪੋਲ, ਇਸ ਦਾ ਡਾਈਪੋਲ ਮੋਮੈਂਟ ਅਤੇ ਇਸ ਦੀ ਵਜ੍ਹਾ ਕਾਰਨ ਬਣੀ ਮੈਗਨੈਟਿਕ ਫੀਲਡ ਬਾਰੇ ਪੜਾਂਗੇ। ਸਭ ਤੋਂ ਪਹਿਲਾਂ ਤੇ ਤੁਹਾਡੇ ਨਾਲ ਇਸ ਲੈਸਨ ਦੇ ਲਰਨਿੰਗ ਆਬਜੈਕਟਿਵ ਸਾਂਝੇ ਕਰਾਂ।
After the completion of this topic, the students will be able to define a magnetic dipole and dipole moment. Describe magnetic field strength due to a magnetic dipole. Discuss the effect on a short magnetic dipole placed in an external magnetic field.
I hope you remember that there are two types of dipoles, electric dipole and magnetic dipole. Today we will study the magnetic dipoles. It is well known that the simplest magnetic structure that can exist is only a magnetic dipole characterized by a magnetic dipole moment. A magnetic dipole consists of two unlike poles of equal strength and separated by a small distance. ਉਦਾਹਰਣ ਲਈ ਬਾਰ ਮੈਗਨੇਟ, ਕੰਪਸ ਨੀਡਲ ਆਦਿ ਮੈਗਨੈਟਿਕ ਡਾਈਪੋਲਸ ਹਨ। ਇੱਕ ਕਰੰਟ ਲੂਪ ਵੀ ਮੈਗਨੈਟਿਕ ਡਾਈਪੋਲ ਦੀ ਤਰ੍ਹਾਂ ਬਿਹੇਵ ਕਰਦਾ ਹੈ। ਇੱਕ ਐਟਮ ਦੇ ਨਿਊਕਲੀਅਸ ਦੁਆਲੇ ਇਸ ਦੇ ਇਲੈਕਟ੍ਰॉन्स ਦੀ ਰੈਵੋਲੂਸ਼ਨ ਕਾਰਨ ਇਹ ਵੀ ਮੈਗਨੈਟਿਕ ਡਾਈਪੋਲ ਦੀ ਤਰ੍ਹਾਂ ਬਿਹੇਵ ਕਰਦਾ ਹੈ। ਤੁਹਾਨੂੰ ਯਾਦ ਹੀ ਹੋਏਗਾ ਕਿ ਇੱਕ ਮੈਗਨੇਟ ਲਈ ਨਾਰਥ ਪੋਲ ਅਤੇ ਸਾਊਥ ਪੋਲ ਦੋਨੋਂ ਦੀਆਂ ਸਟਰੈਂਥਸ ਇਕੁਅਲ ਪਰ ਆਪੋਜ਼ਿਟ ਹੁੰਦੀਆਂ ਹਨ। ਹੋਰ ਮੈਗਨੈਟਿਕ ਡਾਈਪੋਲਸ ਹਮੇਸ਼ਾ ਪੇਅਰਸ ਵਿੱਚ ਹੀ ਐਗਜ਼ਿਸਟ ਕਰਦੇ ਹਨ ਤੇ ਇਹ ਇੱਕ ਦੂਜੇ ਨਾਲੋਂ ਸੈਪਰੇਟ ਨਹੀਂ ਕੀਤੇ ਜਾ ਸਕਦੇ। Also, the distance between the two poles of a bar magnet is called its magnetic length or the dipole length. It is a vector quantity directed from south pole of magnet to its north pole and is represented by vector 2L. Similar to an electric dipole moment, magnetic dipole moment is the product of strength of either pole and the magnetic length 2L. It is represented by vector M. Its magnitude is equal to 2Lm. Magnetic dipole moment magnetic length ਦੀ ਹੀ ਤਰ੍ਹਾਂ ਸਾਊਥ ਤੋਂ ਨਾਰਥ ਪੋਲ ਵੱਲ ਡਾਇਰੈਕਟਡ ਇੱਕ ਵੈਕਟਰ ਕੁਆਂਟਿਟੀ ਹੈ। ਇਸ ਦੀ SI ਯੂਨਿਟ ਐਂਪੀਅਰ ਮੀਟਰ ਸਕੁਆਇਰ ਹੈ। ਪੋਲ ਸਟਰੈਂਥ ਦੀ SI ਯੂਨਿਟ ਐਂਪੀਅਰ ਮੀਟਰ ਹੈ। ਹੁਣ ਤੁਸੀਂ ਨੋਟ ਇਹ ਕਰਨਾ ਕਿ ਮੈਗਨੈਟਿਕ ਡਾਇਪੋਲ ਮੋਮੈਂਟ ਦੀ ਡਾਇਰੈਕਸ਼ਨ ਸਾਊਥ ਤੋਂ ਨਾਰਥ ਵੱਲ ਹੈ, ਬਿਲਕੁਲ ਜਿਸ ਤਰ੍ਹਾਂ ਇਲੈਕਟ੍ਰਿਕ ਡਾਇਪੋਲ ਮੋਮੈਂਟ ਨੈਗੇਟਿਵ ਚਾਰਜ ਤੋਂ ਪੋਜ਼ਿਟਿਵ ਚਾਰਜ ਵੱਲ ਡਾਇਰੈਕਟਡ ਹੁੰਦਾ ਹੈ। Let us now find out the magnetic field strength at a point due to a bar magnet. The strength of magnetic field at any point can be defined as the force experienced by a hypothetical unit north pole placed at that point. It is a vector quantity. The direction of magnetic field strength B is the direction along which hypothetical unit north pole would move if free to do so. Did you notice that we have used the word hypothetical unit north pole simply because an isolated magnetic pole does not exist? To find the magnetic field at a point, we calculate force on this unit pole due to each pole of the dipole and then take the vector sum of the two forces using Coulomb's law of magnetic force and the superposition principle respectively. If minus M and plus M is a pair of magnetic poles, then at any point in space, the net pole strength of the dipole is 0. This does not mean that the field strength of the dipole is 0. So, a magnetic dipole creates magnetic field. Let's know why. क्योंकि north ਅਤੇ south poles एक distance ਨਾਲ separated ਹਨ। ਇਸ ਕਰਕੇ ਐਡ ਕਰਨ ਤੇ ਉਹਨਾਂ ਦੀਆਂ magnetic fields completely cancel out ਨਹੀਂ ਹੁੰਦੀਆਂ। ਹਾਂ, poles ਦੀ separation ਨਾਲੋਂ ਬਹੁਤ ਜ਼ਿਆਦਾ distance ਤੇ north ਅਤੇ south poles ਦੀਆਂ fields nearly cancel out ਹੋ ਜਾਂਦੀਆਂ ਹਨ। Therefore, at large distances from the bar magnet or the magnetic dipole, field strength falls off more rapidly. Let us calculate the magnetic field strength at a point on axial line of magnetic dipole. Let us consider a bar magnet having north and south poles with pole strength plus M and minus M with magnetic length 2L. Here we have to calculate magnetic field strength B at a point P on the axial line of the bar magnet at a distance r from the center O of the bar magnet. If B1 is the magnetic field strength at P due to south pole at S, then magnitude of B1 is equal to mu naught upon 4 pi into M upon SP square. It is along PS. Hence, B1 is further equal to mu naught upon 4 pi into M upon square of R plus L, acting along PO. Let B2 be the magnetic field strength at P due to north pole at N. Then magnitude of B2 is equal to mu naught upon 4 pi into M upon NP square along NP. B2 is further equal to mu naught upon 4 pi into M upon square of R minus L along OP. It is clearly visible that B1 and B2 are collinear vectors acting in opposite directions, and the magnitude of B2 is greater than that of B1. Therefore, the resultant magnetic field strength B at a point P would be the difference of these two field strengths, that is, B would be equal to B2 minus B1, which is equal to mu naught upon 4 pi into m upon square of r minus L minus mu naught upon 4 pi into m upon square of r plus L acting along OP. This is further equal to mu naught into m upon 4 pi into 1 upon square of r minus L minus 1 upon square of r plus L. This gives B equal to mu naught into m upon 4 pi into square of r plus L minus square of r minus L upon square of r square minus L square. On solving, we get B equal to mu naught into m upon 4 pi into 4 LR upon square of r square minus L square. Since magnetic dipole moment m is equal to small m into 2L, therefore B becomes equal to mu naught upon 4 pi into 2mr upon square of r square minus L square. It may be noticed that direction of magnetic field at a point on axial line of the bar magnet is from south pole to north pole, which is same as that of magnetic dipole moment of the magnet. Therefore, in vector notation, vector B is equal to mu naught upon 4 pi into 2r into vector m upon square of r square minus L square. When bar magnet or the dipole is of very small length such that L is much smaller than r, then L square can be neglected as compared to r square. Therefore, for a bar magnet of very small length, magnetic field strength B becomes mu naught upon 4 pi into 2mr upon r to the power 4, or B equal to mu naught upon 4 pi into 2m upon r cube, and the direction is along SP or SN. Let us now calculate the magnetic field strength at a point on equatorial line of magnetic dipole. Let us consider a point P on the equatorial line of the bar magnet or the dipole at a distance r from the center O of the magnet. If B1 is the magnetic field strength at P due to south pole at S, then magnitude of B1 is equal to mu naught upon 4 pi into m upon SP square. It is along PS. Therefore, B1 is further equal to mu naught upon 4 pi into m upon r square plus L square acting along PS. Let B2 be the magnetic field strength at P due to north pole at N. Then magnitude of B2 is equal to mu naught upon 4 pi into m upon NP square. It is along NP. Therefore, B2 is equal to mu naught upon 4 pi into m upon r square plus L square acting along NP. It is clearly visible that B1 and B2 are vectors acting in different directions, but their magnitudes are same. Therefore, to find out the resultant magnetic field strength B at point P, Either we can use parallelogram law of vectors addition, or we can resolve B1 and B2 into their rectangular components. Let angle PSN or angle PNS be equal to theta. Then magnetic field due to south pole, that is B1, has two rectangular components, B1 cos theta along PR, which is parallel to NS, and B1 sin theta along PO, which is perpendicular to NS. Similarly, the magnetic field due to north pole, that is B2, has two rectangular components, B2 cos theta along PR, which is parallel to NS, and B2 sin theta along OP, which is perpendicular to NS. Since the magnitudes of B1 and B2 are the same, and B1 sin theta is along PO, on the other hand, B2 sin theta is along OP. Hence, they cancel out each other. Therefore, the resultant magnetic field strength B at point P on equatorial line of the bar magnet is the sum of the horizontal components of B1 and B2, since both horizontal components are equal and are acting along the same line, that is along PR. The resultant magnetic field strength B would be equal to B1 cos theta plus B2 cos theta, or twice of B1 cos theta, which is equal to mu naught upon 4 pi into 2m upon r square plus L square into cos theta. Since cos theta is equal to OS upon SP, which is capital L upon under root r square plus L square. This gives B equal to mu naught upon 4 pi into 2ml upon r square plus L square raised to the power 3 by 2. Since magnetic dipole moment M is equal to small m into 2L, therefore B becomes equal to mu naught upon 4 pi into m upon r square plus L square raised to the power 3 by 2. It may be noticed that direction of magnetic field strength at a point on equatorial line of the bar magnet is from north pole to south pole, which is opposite to the direction of magnetic dipole moment. Therefore, in vector notation, vector B is equal to minus mu naught upon 4 pi into vector M upon r square plus L square raised to the power 3 by 2. When the bar magnet or the magnetic dipole is of very small length, such that L is much smaller than R, then L square can be neglected as compared to R square. Therefore, for a bar magnet of very small length, magnetic field strength becomes mu naught upon 4 pi into m upon r cube, and the direction is along PR or parallel to NS. Here you can notice that the magnitude of the magnetic field strength at a distance far away from the bar magnet on the equatorial line is half of the magnetic field strength at the same distance on equatorial line. Do you remember the case when an electric dipole was placed in uniform external electric field? Yes, the dipole oscillated in a simple harmonic motion when it was placed in a uniform external electric field. Let us see what happens to a magnetic dipole when it is placed in a uniform magnetic field.
Let us consider a permanent bar magnet of magnetic length 2L, having pole strength M at its north pole and minus M at its south pole. so that this bar magnet has dipole moment capital M, which is equal to M into 2L. Let this bar magnet is placed in a uniform external magnetic field of magnitude B at an angle theta with the direction of B. Force on north pole is equal to MB. Its direction is along the direction of B. Whereas force on south pole is also equal to MB, but its direction is opposite to the direction of B. Since magnetic field B is uniform, therefore net force on the magnet is 0. However, the forces are equal, unlike and parallel since the poles are separated. So the forces act at different points. Therefore, they form a couple which rotates the magnetic dipole or the bar magnet in the clockwise direction. Or in other words, these forces resulting in a torque on the bar magnet. When the net force is 0, the torque or couple is independent of the origin. Its magnitude equals to the magnitude of each force multiplied by the arm of the couple, that is, perpendicular distance between two antiparallel forces. Here, perpendicular distance between the forces, that is, arm of couple, is NA. Since torque is equal to the moment of the couple, therefore torque, tau, is equal to force into arm of couple, which is equal to F into NA, or F into NS sin theta, or MB into 2L sin theta, which is equal to MB sin theta. As torque is a vector quantity, hence in vector form, we can rewrite this expression as vector tau equal to the cross product of the vector M and vector B. The magnitude of M cross B is also MB sin theta, and its direction is normal to the plane containing M and B. However, the direction of torque tau can be obtained by right-handed screw rule. This torque tends to align the axis of the bar magnet along the direction of magnetic field B.
When B is equal to 1 and theta 90 degrees, then torque tau is equal to M. Hence, we may define magnetic dipole moment as the torque acting on a dipole held perpendicular to a uniform magnetic field of unit strength. Unit of M is the unit of torque divided by the unit of B. Therefore, the SI unit of M is joule per Tesla. ਹੁਣ ਜ਼ਰਾ ਇਹ ਦੱਸੋ ਕਿ ਜੇ ਐਕਸਟਰਨਲ ਮੈਗਨੈਟਿਕ ਫੀਲਡ ਯੂਨੀਫਾਰਮ ਨਾ ਹੋਵੇ ਤਾਂ ਕੀ ਹੋਵੇਗਾ? Obviously, ਇਹੋ ਜਿਹੀ ਹਾਲਤ ਵਿੱਚ net force non-zero ਹੋਵੇਗੀ। ਜੇ ਫੀਲਡ M ਦੀ ਡਾਇਰੈਕਸ਼ਨ ਵਿੱਚ ਇਨਕਰੀਜ਼ ਹੋ ਰਹੀ ਹੋਵੇ ਤਾਂ ਡਾਈਪੋਲ ਮੋਮੈਂਟ M B ਦੇ ਪੈਰਲਲ ਹੋਵੇਗਾ ਅਤੇ ਬਾਰ ਮੈਗਨੇਟ ਕੋਲ ਡਾਈਪੋਲ ਮੋਮੈਂਟ ਦੀ ਡਾਇਰੈਕਸ਼ਨ ਵਿੱਚ ਇੱਕ ਨੈਟ ਫੋਰਸ ਹੋਵੇਗੀ। ਜੇ ਫੀਲਡ M ਦੀ ਡਾਇਰੈਕਸ਼ਨ ਵਿੱਚ ਡਿਕਰੀਜ਼ ਹੁੰਦੀ ਹੋਵੇ ਤਾਂ ਡਾਈਪੋਲ ਮੋਮੈਂਟ M B ਦੇ ਐਂਟੀ ਪੈਰਲਲ ਹੋਵੇਗਾ ਅਤੇ ਬਾਰ ਮੈਗਨੇਟ ਕੋਲ ਡਾਈਪੋਲ ਮੋਮੈਂਟ ਦੀ ਆਪੋਜ਼ਿਟ ਡਾਇਰੈਕਸ਼ਨ ਵਿੱਚ ਇੱਕ ਨੈਟ ਫੋਰਸ ਹੋਵੇਗੀ। ਦੋਨਾਂ ਕੇਸਿਸ ਲਈ ਨੈਟ ਟਾਰਕ ਵੈਕਟਰ ਟਾਉ 0 ਹੁੰਦੀ ਹੈ, ਪਰ B ਦੇ ਨਾਨ ਯੂਨੀਫਾਰਮ ਹੋਣ ਕਾਰਨ ਬਾਰ ਮੈਗਨੇਟ ਤੇ ਨੈਟ ਫੋਰਸ 0 ਨਹੀਂ ਹੁੰਦੀ। Let us see some special cases. We know that this torque tries to align the bar magnet in the direction of the field. When M is along B, theta is 0 degree. Hence, torque is equal to mb sine 0, which is equal to 0. This shows the bar magnet in stable equilibrium. While when the bar magnet is held in a direction opposite to B, the torque turns the bar magnet through 180 degree. Thus, the bar magnet will be in an unstable equilibrium. The torque will be maximum when theta is 90 degrees. The maximum value of torque would be equal to mb sine 90 degree, which is equal to mb. The energy possessed by the dipole or bar magnet by virtue of its particular position in the magnetic field is called potential energy of the magnetic dipole or the bar magnet. When a bar magnet or a magnetic dipole of moment m is oriented at an angle theta with the direction of uniform external magnetic field B, the torque acting on the dipole is equal to mb sine theta, which tries to rotate the dipole. Let dw be the small amount of work done in rotating the dipole through a small angle d theta against the torque, which would be equal to tau into d theta, that is mb sine theta d theta. Therefore, total work done in rotating the dipole from orientation theta 1 to theta 2 would be the integration of mb sine theta d theta with limits from theta 1 to theta 2, which is equal to minus mb cos theta 2 minus cos theta 1. When the dipole is initially at right angle to the magnetic field, that is theta 1 is 90 degree and let theta 2 be theta, then the work done would be equal to minus mb cos theta. ਇਹ work done potential energy ਦੇ ਰੂਪ ਵਿੱਚ stored ਹੁੰਦਾ ਹੈ. Since potential energy is a scalar quantity, therefore potential energy U is the dot product of negative vector m and vector b. It is clear that this potential energy would be minimum when theta is 0 degree and maximum when theta is 180 degree. However, there is no potential energy when the bar magnet is held perpendicular to the magnetic field, that is, when theta is 90 degree. Let I be the moment of inertia of the bar magnet when the bar magnet is held at an angle theta in an external uniform magnetic field. Then, in equilibrium, restoring torque is found to be equal and in opposition to deflecting torque, that is, I d2 theta by dt square is equal to minus mb sine theta. For small values of theta in radians, we approximate I d2 theta by dt square as equal to minus mb theta or d2 theta by dt square equal to minus mb theta upon I. इत्थों ਇਹ ਵੀ ਪਤਾ ਲੱਗਦਾ ਹੈ ਕਿ ਇੱਕ external uniform magnetic field ਵਿੱਚ ਰੱਖਿਆ bar magnet simple harmonic motion show ਕਰੇਗਾ. The square of the angular frequency can be obtained as omega square equal to mb upon I. Therefore, the time period t would be equal to 2 pi into square root of I upon mb. With this, we come to the end of today's lesson. Before concluding, let us quickly summarize what we have done so far. A magnetic dipole consists of two unlike poles of equal strength and separated by a small distance. magnetic dipole moment vector m is equal to m into vector 2L. Magnetic field strength at a point on axial line of magnetic dipole B is equal to mu naught upon 4 pi into 2 mr upon square of r square minus L square directed from south pole to north pole. For bar magnet of very small length, that is L much smaller than R, magnetic field strength is mu naught upon 4 pi into 2m upon r cube. Magnetic field strength at a point on equatorial line of magnetic dipole B is equal to mu naught upon 4 pi into m upon r square plus L square raised to the power 3 by 2, directed from north pole to south pole. For a very small bar magnet, that is its length L much smaller than R, the magnetic field strength is mu naught upon 4 pi into m upon r cube. For a bar magnet placed in a uniform external magnetic field of magnitude B at an angle theta with the direction of B, net force on it is 0, but the forces on the two poles of the magnet form a couple which rotates the bar magnet. Torque acting on the dipole is equal to mb sin theta or vector tau equal to the cross product of vector m and vector b. Energy possessed by the magnetic dipole by virtue of its particular position in the magnetic field is called potential energy of the magnetic dipole. Potential energy U is equal to the dot product of negative vector m and vector b. And now let us check how much have you absorbed. My first question is, what is the common word for the separation between two poles of a magnet? The answer is, the separation between two poles of a magnet is known as the magnetic length. The next question is, when a bar magnet is of very small length, then what would be the magnetic field strength along its axial line? The answer is, magnetic field strength at a point on axial line of magnetic dipole B would be equal to mu naught upon 4 pi into 2m upon r cube. ਆਸ ਹੈ ਕਿ ਅੱਜ ਦਾ ਇਹ ਮੈਗਨੈਟਿਕ ਫੀਲਡ ਡਿਊ ਟੂ ਅ ਮੈਗਨੈਟਿਕ ਡਾਈਪੋਲ ਦਾ ਕਨਸੈਪਟ ਤੁਹਾਨੂੰ ਸਮਝ ਵੀ ਆਇਆ ਹੋਵੇਗਾ ਅਤੇ ਇਸ ਵਿੱਚ ਦਸੀਆਂ ਗੱਲਾਂ ਯਾਦ ਵੀ ਰਹਿਣਗੀਆਂ। ਅਗਲੀ ਕਲਾਸ ਦੀ ਉਡੀਕ ਰੱਖਣਾ। ਉਦੋਂ ਤੱਕ ਗੁੱਡ ਬਾਏ।